All right, buddy. Today's class recording has started. Good? Well, too late, but just gotta take your phone. So yesterday, we started talking, or we got in more detail into the structure of an atom. But our understanding of the structure of the atom is a result of a couple different experiments, a couple different things as we go along the timeline, right? So the first idea of atoms comes from where? Who first proposes this idea of an atom? Democritus, all right? He first proposes the idea, right? But Eric, what does Democritus lack? Backing evidence, experimental evidence to back up his idea, right? That's why his idea and Dalton's idea are pretty much the same, but Dalton has evidence to back it up, right? So, Dalton proposes our first atomic theory, the idea that atoms exist. What does Dalton say about atoms? What are a couple of things that Dalton says about atoms? Alec, what's one thing? They're indestructible. They're the smallest things out there of matter. What else? They're all identical if we're talking about the same thing, right? They have a definite mass, but that mass is different than the atoms of other things, right? And there's one more thing that's going to be kind of important today. They have no electric charge, and that's going to be important for today especially, all right? Good there? All right, Thomson, okay, J.J. Thomson. First, what experiment does Thomson do? The cathode ray tube. And the gist of the cathode ray tube experiment is that Thomson figures out that there are what? Negatively charged particles, which we call electrons, all right? Then Rutherford, with the help of some other people, does the gold foil experiment. What does the gold foil experiment introduce to our understanding? The nucleus, right? That all the positive charge of an atom is condensed in a real small spot and the electrons move around it. Good there? That like, you need to know those things about those scientists and those experiments moving forward. Okay? All right, so the outline that we talked about yesterday, we introduced or we described the three main subatomic particles that you are going to be responsible for in this class. There are lots of other subatomic particles that we won't discuss in here that gets us to a whole nother level of understanding. So right now you're just going to be responsible for three of them, all right? And this chart summarizes those three subatomic particles, all right? And you have that chart on the second page of your outline. So, all right, go ahead and let's write that down for now, and then we'll discuss what it means. Yeah, real small. All right, so let's discuss this charge just a little bit. First, these are all subatomic particles, meaning what? They're smaller than an atom. They are things that make up atoms, all right? So, we know that there are three main ones we'll talk about. First, I hope the symbol makes sense, right? The first letter is obviously just the first, or the letter is just the first letter of the word itself, right? What is the subscript representing? Charge. What kind of charge they have, right? Okay. Electrons have negative charge, protons have positive charge, neutrons don't have any charge, right? So the next column, on your outline, in your outline it just says charge, but mine says relative charge. When we talk about relative, we label something as relative, what are we doing? You're comparing it, all right? Notice that there aren't any units in this chart, okay? When it says charge, that's actually not a measurement. It's a comparison between those three particles, okay? So, you can see that under neutron it has zero charge, right? The fact that electrons are negatively charged and protons are positively charged is true, but how does that charge compare to the other one? They're equal. All right. Make sure that we have. I know you know. Yeah. Just want to make sure that we have everybody. I think we got it. So electrons and protons have an equal amount of charge. Just one's positive and one's negative. So what will they do to each other? Basically cancel each other out, right? Okay. Then the farthest column on the right, it says relative mass. Yours said, like one thing you might do is that on your chart, in your outline, you might add relative to the charge column, just so you know that that's not a measurement. Like it's not. We can't. If you measured the charge of an electron, it wouldn't come out as -1 anything. That's not an actual measurement. It's just a comparison, right? And then same thing for the last column, right? So if we're comparing relative masses, what are we seeing about the size of protons and neutrons? About the same, right? Neutrons are a little bit bigger, but they're about the same, right? But then what are we seeing about the relative mass of the electron? Real small, right? Like you need almost 2,000 electrons just to equal the mass of one proton. So we can see that when Rutherford told us that a large majority or a large percentage of the mass of the atom is in the nucleus, right? What's in the nucleus? Are the electrons in the nucleus? No. What's in the nucleus? Protons and neutrons. And we can see from this chart that's why, right? Because neutrons and protons are about the same mass as each other, but much, much, much bigger than electrons. Okay? Good there? Okay. All right. That being said, let's talk about how atoms differ from one another. Dalton is right in that atoms of one element are different from another element. Oxygen atoms are different than carbon atoms. Carbon atoms are different than iron atoms. Iron atoms are different than sodium atoms. But how are they different? And so that's what we're going to get into here today. First, we need to know an element's atomic number, right? The atomic number tells us the number of protons that the atom contains. Well, how do we know that? Well, we look on the periodic table. Okay? So, does everybody have their periodic table handy? Yeah. Okay? So I'm going to get out of here and pull up my periodic table. Okay? So you can see here that on my periodic table, okay, in each square there are two things. There is a symbol, either a one-letter or two-letter symbol, and then there is an integer number, right? A whole number. Okay? You guys have that. You might have a little more information than that, but you definitely have those two things. All right? So on my periodic table, this integer number, notice it starts up here in the top left, number 1, all the way over to the top right, number 2. I should do this here so that people watching the video, right? So here's number 1, right? Here's number 2. Then it comes back here, number 3, number 4, 5, 6, 7, 8, 9, 10. And as you go across the row, it just goes up by 1. Okay? That integer value is the atomic number of that element. Okay? It is what distinguishes that element from every other element. Because the number of protons identifies what kind of an element that atom is. Atoms of different elements will have a different number of protons and different atomic numbers. This is how we distinguish one atom from another. The number of protons. There may be things about atoms that are similar. We'll explore those things a little bit later on in some units coming up. But if they have different numbers of protons, they are different elements. And if they have different numbers of protons, they have different atomic numbers. Okay? Good there. That's the first important point for today. Okay? So when you look at the periodic table, in each square you will see, if you're using the periodic table in your book, it is the first number in the square up at the top, right? if you're using something on your phone, there should be an integer number that shows up in every square. It goes up by 1 as you go across the row. Okay? Good there? All right. Joanna, what's one of the things that Dalton said about atoms? What did you tell us that atoms? They have no electrical charge. We know that protons have positive charge, and the atomic number tells us the number of protons. But if an atom has to be electrically neutral or no charge, what has to be true about the number of protons and the number of electrons? They have to be the same. So the number of electrons is also equal to the atomic number because whole atoms are electronically neutral. That's one of the things that Dalton said about atoms in his atomic theory. And that means they have to have the same number of protons and electrons. And that means the atomic number tells you the number of protons, but it also tells you the number of electrons. Now, this is for a whole atom. We will find as we go along that the number of electrons will change a lot. And we'll talk about why they change as we go along, and that gets us into bonding and stuff like that. We're not there yet. Right now, if we're just talking about an atom of oxygen, it will have the same number of protons and the same number of electrons. Okay? Good for now. Okay, so this is how we tell atoms apart, but there's a third part of the atom, and that's the neutron, right? So getting into that, that gives us the mass number, okay? All right, notice on your periodic table, okay, if you're using the one in your book, okay, you'll see that there are 4 things in each square, right? You have the atomic number, you have, wait, let me do this, hold on. Stand by. Let me see if I can do this real quick. While you guys are looking at your book, maybe I should have it up too. So, some of you aren't, obviously. What? I do, but it's not the one from the book. I want to show people like the one from the book, so if they're looking at the book, they can understand what I'm talking about. What page in the book are we? For those of you, is anybody looking at the actual page in the book? All right, let me check and see if it's back here. 718. It's okay. Oh, this one has the Earth and space science in it. This is a different version of the book. That's okay. Let's see if it says N. Let's see if I put in N. Let's see what that does. No, it doesn't. 1,000. You would think. Let's see if the skills handbook, appendices, SI units, weather map. Is that it? No, that's, well, kind of is what we're looking for, but not exactly. Hold on. It's in here, so we could go there. That would work too. Somebody look at, never mind. I'll find it. Does somebody look in chapter 5 and find out what page it's on? Not quite. There we go. So I could have done that too. So. All right. So this is only half the periodic table, but it will make my point for me. So yeah. So when you guys are looking at your periodic table, and that would have worked actually. Like to just search the periodic table. All right. When you look at the periodic table, there's going to be, generally speaking, at least 3, but usually 4 things. Sometimes there will be more than that, but there's going to be at least 4, right? So you're going to have the integer number. That's the atomic number. We said that tells us number of protons. You're going to have the symbol. A lot of times you're going to have the name as well. But then there's going to be a second number, and a lot of times that number is a decimal, like it says here, okay? So if we go up to the legend, of course, isn't on this page. There it is, okay? So if you go to the legend, right, you'll see that that decimal number that shows up is labeled as the atomic mass, okay? The atomic mass is not the same as the mass number, okay? So don't make that mistake that you can find the mass number on the periodic table. It doesn't show up on the periodic table. And here's why. So we know from which experiment that a large majority of the mass of the atom is located in a nucleus. Which experiment told us that?
Rutherford.
Rutherford. And he did which experiment?
The gold foil.
Gold foil. Okay? And so Rutherford's gold foil experiment tells us that a large majority of the mass is located in the nucleus. And we know that protons and neutrons are in the nucleus. So the mass number tells us about the mass, but it doesn't tell us the mass. Okay? It tells us the number of protons plus neutrons in the nucleus. Is the sum of the protons and the neutrons, the number of protons and the number of neutrons. Okay. Basically, mass number is a count of the number of protons plus the number of neutrons. Meaning, if we are just counting protons and neutrons, what is the mass number always going to be? Not necessarily. But if we're just counting, it has to be what kind of a value? An integer value. It is not going to be a decimal point or a decimal value. That number on your periodic table is not the mass number. It's something different. We'll talk about what it is later on. But don't look on the periodic table and find that number, that decimal number, and write it down as the mass number. That's not what it is. The mass number is a count of protons plus neutrons. Okay? Good there? So why is that important? Because what we have found is that certain elements come in different forms. Okay? These different forms we call isotopes. Isotopes are atoms that have the same number of protons, but a different number of neutrons. If they have the same number of protons, what does that mean is the same for both of these atoms? The atomic number is the same. But if they have a different number of neutrons, what will that make different? The mass number. So, they're same element with a different mass number. They have the same atomic number, but they have different mass numbers. Okay? One of the points of Dalton's atomic theory was that all atoms of the same element are identical. Not true. We find that there are certain atoms out there that have the same number of protons but a different number of neutrons. They're still the same atom, they're still the same element because they have the same atomic number, but they are not exactly the same. Okay? So, parts of Dalton's atomic theory are true, some are not. All right? Okay, so how do we tell these things apart? Well, there's a couple different ways. One way is this system here where we have an element name and then we put a dash and then we put the mass number afterwards. Okay? For example, let's take a look at the sheet that I gave you today. Okay. 1, 2, 3, 4, 5. In the fifth column down, we have boron 11. Okay? Boron 11. So, let's fill in this row together. So, you're going to look on your periodic table, and you're going to find boron. All right?
You know what number that is?
I know what number it is, but I want you to look for it and find it. All right? So, all right, so here's boron, atomic number 5. So that should give you three columns on the sheet that I gave you, right? One of the columns is straight up atomic number. So the atomic number of boron, we looked on the periodic table, is 5. So we're going to put a 5 in that spot right there. All right? Okay. So let me do this. The 5 is going to go there. I'm going to turn that red so I know that. Okay. But if we know the atomic number, what else do we know? The number of protons, but also the number of electrons. So this column here is 5, but then this has to be 5, and this has to be 5 as well. Why did the number of protons and the number of electrons have to be the same? So the charge is neutral. Okay? All right. Now, two ways we can figure out the mass number. What did we say the mass number is? What does the mass number tell us? Sum of protons and neutrons. So, if we look here, right, we see that there are 5 protons and 6 neutrons. So what is the mass number of this atom? 11. So that's going to go right in here in this column, right? The mass number is 11. But we could have skipped that step just by looking at this name of the isotope. The isotope tells us, the name of the isotope tells us what kind of an atom it is, boron, but then its mass number, right? That 11 afterwards is the mass number. So we can tell how many protons it has by knowing what kind of element it is, but then we can also tell how many neutrons it has by subtracting the subtracting the atomic number from the mass number. Good there? So going back to your outline, all right, let's take a look at this one, okay? Oxygen 16, okay? The fact that it's oxygen tells you how many protons it has. So where are you going to find out how many protons it has? You're going to go to the periodic table and find the atomic number of oxygen. What is the atomic number of oxygen? 8. So it has 8 protons. All right? This is on your outline if you notice that it's right there. Okay? Okay. But that 16 that follows it is the mass number, which is the sum of the protons and the neutrons, right? So if you know that the sum is 16 and there are 8 protons, what does that mean about neutrons? There has to be 8 neutrons as well, okay? And even though it doesn't say it up on the board, there's one more thing we can tell about this atom. What else could we tell about this atom, Frank, because you already wrote it down?
8.
It also has to have 8 electrons as well. All right? Good there? Still on your outline, chlorine 35. So let's find chlorine on our periodic table. Joe, chlorine is where on the periodic table? Atomic number 17 over on the far right-hand side. So that tells you what about it? Number of protons and the number of electrons, right? Protons and electrons always have to be the same. So 17 protons and 17 electrons. How many neutrons?
18.
18 neutrons. And you did that by doing what? Subtracting. How about not the atomic mass, the mass number? Okay. 17 protons, 18 neutrons. We don't always have to have the same number of protons and neutrons, right? Here's a pretty dramatic example of this. Uranium 238. Uranium 238. Find uranium on the periodic table. It's a big one. Yep. Atomic number of uranium 92. Okay. Way down at the bottom. Okay. We have to do a little math here. Right? So it has 92 protons. But that means it also has to have 92 what? Electrons as well.
I'm using my head. It's 146. Oh, yeah.
Everyone see where we got, everyone understand where we got 146 neutrons from? All right. That's one way we can distinguish isotopes from each other. All right? One other way that we can distinguish isotopes from each other is using the atomic symbols. Okay? So, this is a generic version of the symbol. It does not represent any element in particular. Okay? But we start off with the symbol itself. We usually make that a big symbol. Okay? One thing that I will start marking you off on from now on, all right? Chemical symbols. If they are one-letter symbols, they are always capital letters. If they are two-letter symbols, the first one is capitalized and the second one is lowercase, right? Don't write chlorine, capital C, capital L, all right? What? No, I won't make you memorize them, but if you write them wrong, I will mark you up. Okay. All right, elemental symbol, X. Okay, in the X spot. There is no element X on the periodic table, it's just a placeholder. Okay? All right. Letter Z represents the atomic number. Now, I know what you're going to say. Why is Z the atomic number? Why isn't A the atomic number? I don't know. I didn't make that decision, so don't yell at me on that one. Okay? And then the letter A represents the mass number. Represents the mass number. So using this notation, if we go back to the worksheet, let's take a look at the second row. Let's take a look at the second row. All right, so from this symbol, right, we can tell two things right off the bat, right? That and that, right? The bottom number in this symbol represents the what? The atomic number. So that should give you 3 columns in this table, right? If the atomic number is 2, obviously that means the atomic number is 2, right? But it also means the number of protons is 2. But it also means what else is 2? Number of electrons. Okay. The top number in this symbol represents the what? The mass number. So we can go straight up and fill that as 4. But if we know the mass number and we know the number of protons, we can also figure out the what?
Neutrons.
Neutrons. The number of neutrons in this atom is 2. Protons and neutrons don't always have to be the same. They just are in this case. All right? So we've got this symbol, but we said there's another way that we can represent isotopes, and that's with the name and the mass number. So what would we call this isotope? Helium-4.
This would be an isotope, that would it be?
Say again?
Would this be an isotope?
They're all isotopes. There isn't one that is, so, Jack, there isn't one that is like, okay, this, here. Okay. Those atoms are isotopes of each other. There isn't one that's like the standard form and the rest are isotopes. Those are, you have to have more than one to have an isotope because isotopes are the same protons but different neutrons. So it's not like one's normal and the other ones are different. we'll find out that some of them show up more often than other ones, but it's those two are isotopes of each other because they have the same protons and different neutrons. Right, good. Or we could have something like this. Okay? These three are all isotopes of each other because they all have the same number of protons because they're all carbon, but then they would have different mass numbers. So yeah, all three of these are isotopes. So it's not just two, it's not just three. Any atoms that have the same protons with different neutrons are isotopes. There's some elements on the periodic table that can have like 5 or 6 isotopes. Like zinc has, I think zinc has like 5 isotopes. So, you know, just... All right. Good so far? All right. Do you want the last 5 minutes to work on the sheet?
Yeah.
Go ahead. Just work on it together. I'll tell you what. With about 2 minutes left in the period, I'll put the answers up on the board so you can see how you're doing. Go along, all right? Carry on. Work together. Figure things out if you need to. And I'll show you the answers with about 2 minutes left in the period. All right, buddy. As we're getting close here to the end of the period, I'll tell you what I'll do. I will post the answers on Google Classroom, so you can check it out there, and I'll have the answers there so you can check and see how you're doing. There is a little bit of this on the quiz that I posted today. Quiz is due on Friday, so if you need a little bit more practice, if you want to talk to me a little bit about it, check your answers. That's fine. Quiz isn't due until Friday. Tomorrow, we might review this a little bit, and then we'll get into the lab right away tomorrow, so you have time to get that done. Okay? So if you have questions, come and see me.
We do the